Okay, so we're happy to have Maximilian Stegemeyer from Freiburg, and he will be speaking today about intersection, multiplicity in loop spaces, and the string topology coproduct.
All right, yeah, thanks so much for the introduction, and thanks for the invitation to the seminar. Yeah, so let's just dive right in. So first, I want to say on the next slide what string topology is, although I assume that probably people have heard many talks about this. And then I will explain what I actually will speak about in this talk. So, I mean, in the setup that I'm considering, we consider closed-oriented manifolds, and then the free loop space lambda m. Yeah, so these are all curves in M. Yeah, so I mean they close up. Yeah, and I want to have some regularity condition for two reasons that I will make clear later. So I wrote gamma is of class H1, subol of class H1. So this means that the curves are differentiable almost everywhere and have a square integrable derivative. And I mean, the nice thing is that this is in a Hilbert manifold. So some things like talking about submanifolds and their tubular neighborhoods and normal bundles and all these things make sense. And but of course you can. I mean, this version of the free loop space is homotopy equivalent to the continuous version of the free loop space. Yeah, so just the continuous loops in M endowed with a compact open topology. All right, and string topology well studies algebraic structures like coproducts or products on the homology of the free loop space. And well, the most well-known structure, or the most prominent example, is the Sullivan product. Yeah, so this is an honest product on the homology of the free loop space. This degree shift minus n, this is the dimension of the manifold, and well, this is kind of what got this whole business started. And in this talk, I will mostly talk about the Goresky-Hingston coproduct, or I mean, I think in the title of the talk I called it string topology coproduct. And yeah, so this is a map in homology from this relative homology. Yeah, so here the constant loops, the M sits inside the free loop space as the constant loops, and then I mean in this way I wrote it down. It's just a map in homology which goes to this kind of weird relative part here. But actually, if you look closely, it's kind of the product of the pair lambda m times m. Yeah, the product of these topological pairs. And so there's a lot of interest also in recent years. There was lots of interest in this Goresky-Hingston coproduct, and in this talk I want to kind of show how you can use like quite geometric ideas of looking at self-intersections of loops or making some statements about the coproduct. Yeah? And this is where this notion of intersection multiplicity comes in. And I mean, okay, I don't have a kind of an outline, but you can see it on the top line. So I will talk about intersection multiplicity, and in the end, I will in particular talk about this in the case of for Lie groups and where I use a very geometric approach, geodesic curves in manifolds. So then I will also give a quick introduction to this or overview over this topic.
Maximilian,
right,
a quick question: do we care about what kind of coefficients are you taking homology with?
I mean, I think I will always make it clear, but I mean, I'm not only field coefficients. So that's why I wrote it down this way. I mean, maybe let me switch to the next slide. No, sorry, this will come later. Yeah, I mean, of course, if you have field coefficients, then you can actually, by the König isomorphism, you can go to the tensor product of this homology with itself. Then it looks much more like a coproduct. But yeah, if you take, in general, if you take Z coefficients, then I mean, the best thing you can do is you end up in this in the homology of this pair. But yeah, I think I will talk a bit more about this, so hopefully it will become clearer. Okay, but so first I want to give kind of a definition of the coproduct, maybe not with all details, but of course I want to talk about the main idea. Yeah, so what we look at is the space of loops with self-intersections. Yeah, but in a parameterized way. Yeah, so here I look at the space F. So these are pairs, loops, and a time in the unit interval, such that this loop closes up. Yeah, so sorry, it doesn't close up, but has a self-intersection. Yeah, so I have a loop with a basepoint self-intersection. Yeah, so here we don't look at any at arbitrary intersections of the loop, but at basepoint intersections. Yeah, and then we also remember the time where this happens. Yeah, and well, this is obviously a subspace of lambda times the unit interval, and in a certain way it behaves like a codimension n submanifold. Not quite, but it's basically good enough for one thing we want to do, which I will talk about next. And then we have an obvious map from this space F into the product of the free loop space with itself, yeah, which just maps this loop where we remember the self-intersection time, and well, then you take the first part and you take the kind of second part, yeah, and then you get two pairs of loops. You get a pair of loops, sorry. Okay, and so yeah, we get this diagram. So we have this cutting map, and we have this inclusion here, and now we want to get something in homology, and we. Oh, sorry, I'm sorry about all the drawing that I will do. Kind of my setup is new, and I'm not so familiar with this drawing board. So to get something reasonable in homology, we want an arrow in this direction, and indeed this can be done with if you use something which is called a Giesen map or Tom map, or people have different names for this. And I don't want to tell you how exactly you can construct this, but this can be done. And then this Goresky-Hingston coproduct is defined as the composition. So we start in this relative homology, free loop space relative to the constant loops. Then we cross with the unit interval. Yeah, so I is the positively oriented generator of the first homology, yeah, of the unit interval relative to its boundary. Yeah, so you can cross with that. I'm taking arbitrary coefficients at the moment here. And well, then you end up in, again, a relative homology of this space lambda times the unit interval. And as I said, so this F almost is a codimension n submanifold. So for these situations, there are these Giesen maps. And then because it's codimension n, you get the degree shift minus n. And then you can apply the cutting map here, and then you end up in this homology of the free loop space times itself relative to this term in the end here. Yeah, so up to me telling you how this Giesen map works exactly, this is the definition. And so as already announced, so if we take field coefficients, or of course in certain situations where we are where the homology is free or something like this, then we can actually compose with the Kinnet isomorphism to end up in this tensor product here. Yeah, and of course this looks much more like something that we would call a coproduct. Okay, and yeah, dually, in a sense, dually, one can define the Goresky-Hingston product, yeah, which is a product in cohomology, or again in relative cohomology relative to the constant loops. And I mean, historically, this is what people study first. I mean, this is actually what is called the Goresky-Hingston product. And for example, if your homology is of finite type and you take field coefficients, then these two operations are really dual to each other. And otherwise, it's maybe more like a moral duality. But yeah, usually, if you know something about the one thing, then you can also say something about the dual object, of course. And well, I mean, maybe one more justification why we should really call this a coproduct is the following theorem by Nancy Hingston and Natalie Wahl. And well, this Goresky-Hingston coproduct is graded co-associative and graded co-commutative. Yeah, and it is not co-unital. Yeah, it cannot be. It's not co-unital already for degree reasons. It cannot be co-unital. And okay, graded co-commutativity sounds quite good. Of course, what's a bit strange here is that I had to say graded co-associative. Maybe a general word of caution here. So what I did not mention in the definition is that there are, of course, signs involved. And of course, signs are very messy. And yeah, I don't really want to talk about this here, but keep in mind that so this, well, this is maybe also some kind of, if you want, efficiency of this coproduct, that it's only graded co-associative. All right, and well, for this talk, I also need to talk about a based loop space version of this coproduct, which is very straightforward now to define. So if you look at the based loop space, yeah, so omega m for some fixed base point, then this is certainly a subspace of the free loop space. And we can basically well, do this whole construction also for the based loop space. So we can look at the space f omega. Yeah, so now these are based loops which have a base point self-intersection at some time s. And of course, then the cutting map restricts to a map into the product of the based loop space with itself. And again, this behaves. I mean, this space here inside omega times I. This behaves like a codimension and submanifold. And so you can similarly define what I will call the based coproduct. Simply based refers to based loop space. And again, if you do it in the setup, then you get a map into the homology of the product of the based loop space with itself relative to this term in the end here. Yeah. And of course, so one thing is so here is a diagram where you see that it behaves in exactly the kind of the way that you would expect. So so jota here is the inclusion of the based loop space into the free loop space. So sometimes I will write omega instead of omega m, and lambda instead of lambda m. And okay, then here we have a map in homology from this reduced homology into this homology where we have defined the Goresky-Hingston coproduct. Then here we do the Goresky-Hingston coproduct, and on this side we do this based coproduct. And here again we have the maps induced by the inclusions, and indeed this commutes. Yeah, so okay, this is kind of what you would expect here. And of course, this map in homology here, so this one, this is in some situations actually injective, but in general it's not, and usually it's far away from being surjective. Yeah, so okay, you could say, okay, maybe this base coproduct doesn't tell me so much if I'm actually interested in the coproduct on the free loop space, but so there's a result by Leonard Meyer, and this gives maybe a stronger relation between these two objects. So if we consider the free loop vibration, which is just the evaluation, so we evaluate the loop at its starting point or base point, basically. This is well known to be a vibration, and then we take coefficients in a field. Well, then of course to this free loop vibration we have an associated Serre spectral sequence, and because we're dealing with relative homology, you need a certain relative version. And this can be done, and indeed it converges to this relative homology, and this can be endowed with a co-multiplicative structure. I don't want to say what the co-multiplicative spectral sequence is, but it's kind of exactly what you expect it to be. So on each page of the spectral sequence we get coproducts, and okay, so there are also some degree shifts happening here, but I don't want to go too much into the details here. And well, now of the E2 page, there's an identification, with since we take coefficients in a field with a tensor product of the homology of the base, with the homology, this relative homology here, so the reduced homology of the fiber, and the fiber is the base loop space, and then under this identification, this coproduct on the E2 page is identified with, so on the base we take the diagonal map, and on the fiber we take this based coproduct. So here this based coproduct shows up, and then the statement is that this co-multiplicative spectral sequence converges to the Goresky-Hingston coproduct. So on the E infinity page, we have a coproduct which is induced by the Goresky-Hingston coproduct. So we see that this base coproduct then, in a sense, tells us quite a lot about the Goresky-Hingston coproduct. And in particular, in my talk, I will actually have many results. Where we show that this base coproduct is trivial, and then of course here we already have the coproduct on the E2 page. We have that this coproduct on the E2 page is trivial, and then also of course subsequently on all the other pages, and so this kind of gives quite a strong restriction. If we show that the base coproduct is trivial, this gives quite a strong restriction kind of for what the Goresky-Hingston coproduct can do. Of course, from the triviality of the coproduct on the E infinity page, it doesn't follow that the coproduct is trivial, but in some sense, it's quite a strong restriction then to what it can do.
Maximilian, I have a question. Do you need some sort of simple connectivity hypothesis in this theorem?
Oh yeah, sorry. I mean, of course I guess. Sorry, I didn't look this up well enough. So maybe let's add. Simply, I mean, of course, you want the Serre spectral sequence to work well. I mean,
so you want this E2 page splitting as a tensor product, right? So, I mean, the question is if the result is still true when you have a non-trivial action of pi1 here, like.
Well, that I don't know.
I don't think it's true actually. If you know if the E2 page is homology of M with coefficients in the local system, then I don't.
That's a good point, of course. Yeah. So yeah, I actually yeah, I probably should add this hypothesis. Yeah. All right. Okay, so anyway, this was just kind of as a justification why, I mean, of course, we can be purely interested in this based coproduct, but I mean, I will have one result about this based coproduct where I can show that it's trivial, and then at least in certain setups, like in a simply connected setting, then it gives us also some information about the coproduct on the free loop space. Okay, so well, now I should of course mention, or I want to mention, the most exciting recent result in about this coproduct, and this is the non-homotopy invariance. Yeah, maybe I want to quickly mention that this Sullivan product was quite soon after it was introduced. It was shown that it's homotopy invariant, and but kind of one hope in string topology was to find something which can detect more than the homotopy type. And indeed, Florian Neff showed in 2021, it made some explicit computation with length spaces, and this computation shows that the Goresky-Hingston coproduct is not homotopy invariant. And well, I mean, last year, so 2024, I mean, this is now there's a theorem now that says exactly how the failure, or what the failure is of the coproduct to be homotopy invariant. And well, I quickly want to state the theorem, maybe a bit roughly, and this is by Florian Neff and Pavel Safronov. And well, it says that if we have a homotopy equivalence between closed-oriented manifolds M1 and M2, and then we look at the Whitehead torsion, yeah, this lives in the Whitehead group of the fundamental group, and there's a map which is, as far as I understand this, I'm not an expert in this, but the Dennis trace map is a map which is defined via Hochschild homology, but well, we know that there's a connection between Hochschild homology and the free loop homology, so we can look at this as a map from the Whitehead group to the first homology of the free loop space relative to the constant loops. Yeah, well, this is the Dennis trace map, and so the Dennis trace of the Whitehead torsion shows up in the equation. And okay, now it gets a bit technical, but I quickly wanted to write this up. So there are two maps, the L and the R. Yeah, from the free loop space to the product of the free loop space with itself, and then then you look at the induced map in homology, and you plug in this Dennis trace of the Whitehead torsion, and then you get out something, yeah, some tensor product here, and also back here, and well then, so what is the point here? Well, we want to look at this difference, right? We want to compare. Okay, first we go with F to M2, yeah, with our homology class here, and then we do the coproduct on M2, and we want to compare this to, okay, we first do coproduct on M1, and then we go to M2 with F, yeah, and then it turns out that, well, the right-hand side of this equation, well, this features now this mu L and nu L, which comes from the Dennis trace of the Whitehead torsion, and then here you somehow need to take the Sullivan product with F star of X, and then here you need to do it kind of the other way around. Yeah, so I mean, it's not super important what we have on the right-hand side here. I just wanted to mention that there's an explicit formula now for this. And well, so I mean, we already know that in general the coproduct is not homotopy invariant, but since we have this formula, it shows that the coproduct is actually simple homotopy invariant, right? Because if this homotopy equivalence is simple homotopy equivalence, then the Whitehead torsion vanishes, yeah, and then of course we have 0 on the right-hand side. Yeah, and I should also mention that so there are two other versions of the theorem, one by Koenigsberg and Porcelli, and one by Nathalie Wahl, and they all have the formula. They all have formulas which look similar to this, but if you look at it in detail, then actually what they have on the right hand side, it's not, at least not a priori, clear that it agrees. So yeah, but of course it's very nice that there are some results now about this. Sorry, is there a question? Okay, then I'll continue. And okay, so basically so much about as an introduction, and maybe one last word about, I mean, okay, maybe we should also think a bit about examples, how this coproduct actually behaves. Yeah, so so for spheres and projective spaces, yeah, at least quaternionic and complex projective space, the Goresky-Hingston algebra is finitely generated, and I already want to mention this here. So there exists a non-nipotent element whose powers correspond to the iteration of prime closed geodesics. Yeah? So this is actually basically already in the Goresky-Hingston paper. They consider these spaces, and as far as I understand, this was at least Nancy Hingston's idea to look for such a product in cohomology, which resembles this iteration of closed geodesics. Yeah, so I will come back to closed geodesics later. And and here also the Goresky-Hingston product behaves very similarly to the Sullivan product. And in the rest of the talk, we will actually see many instances where the Goresky-Hingston coproduct and also then the product is trivial. And I personally found this a bit surprising. It is known that the Sullivan product usually is non-trivial and interesting. And I will show you many results or several results actually where the coproduct is just completely trivial. Yeah, recall that it's not co-unital, so it can just be zero.
Can I ask a quick question? Are there other like compact symmetric spaces? Because like the examples that you were talking about earlier, like the projective spaces and the sphere, they're all compact symmetric spaces, but they're like real rank 1.
Yes, I will come to symmetric spaces later. Yeah.
Okay. So, great.
Yeah, thanks. Exactly. These are the rank 1 spaces, and in some sense, there seems to be something seems to be going wrong if you go to higher rank. But I will come to this later. Yeah, thanks. All right. So, first, now I want to introduce this notion of intersection multiplicity. Yeah, and I want to recall that the coproduct cuts loops apart at points of self-intersections. Yeah, if we have a base point self-intersection, then this coproduct kind of can detect this and cut it apart. At least that's the intuition behind the definition. And actually, on this slide, I want to show you that this can actually be made precise in the following sense. Since I have intersection multiplicity in the title of the talk, I wanted to give the proper definition. So as usual, we look at closed-oriented manifolds and then at homology classes in this relative homology. Yeah, then you have this relative chain here X, and you choose a chain small x which represents this. Then the intersection multiplicity of this homology class is defined as follows. So we take the infimum over all cycles representing all kind of relative cycles representing X. And in each cycle, now we can look at the image, and then we take the non-trivial loops. Yeah, so we take all loops in the image which are not in the constant loops, and then we count the base point self-intersections. Yeah, so this just counts. You look at the image of a cycle, and you look at all loops, and you count the base point self-intersections, and you take the supremum. Yeah, and so since my loops are defined on the unit interval, I always count the trivial base point intersection twice. So that's why I subtract -1. Yeah, so. I don't know if a sketch helps, but so here we count. So this has a self-intersection here, in particular at time 0 and 1. Yeah, so that's why I want to subtract 1 to not count this twice. And then I don't know. This is at 1/3. I have a second self-intersection here. And this is a definition you can make. And now kind of the idea is that if we have kind of very low intersection multiplicity, then there's not so much to cut apart, and then the coproduct should behave in a certain way. And this is made precise by Nancy Hingston and Natalie Wahl, and they show the following. So if we have such a relative homology class and the intersection multiplicity is less or equal than some k, then the case iterated coproduct is trivial. Yeah, and so case iterated coproduct is defined like this, and if you do the coproduct, then you end up in the homology of you have a pair of loops, and so then you can apply either the coproduct to the first loop or to the second loop, and here I wrote down you always apply to the last loop, but by co-associativity it doesn't matter where you put it, at least up to sign, but for this triviality statement it doesn't matter where you put the coproduct. All right, and the analogous results the result also holds for the base loop space. You can make this definition in exactly the same way, and then this proof also carries over to the base loop space. And now kind of a question that I want to talk a bit about is maybe can we just find some situations where the intersection multiplicity is simply 1 for all classes? Yeah, and I mean, of course, the answer will be yes, and so I will present a few results where we can simply show that for all homology classes we have intersection multiplicity 1, and then we immediately get, right, then it immediately follows that the coproduct is just trivial. Yeah. Okay. And all right, so the first thing is about product spaces. Yeah, so this is some of this results in this talk are based on joint work with Philip Cooper. And so yeah, let's talk about this now. Take two closed-oriented manifolds, M1 and M2, both with vanishing Euler characteristic. And then we look at the product manifold. And then we can show that for each relative homology class in this relative homology, this has intersection multiplicity 1. And as I said, consequently, the Goresky-Hingston coproduct on n vanishes. Yeah, and I mean, the proof is kind of, yeah, very, very naive and very simple, but I mean, yeah, I still think it's maybe interesting to look at this. So, okay, since we have trivial Euler characteristic, we can take nova vanishing vector fields, yeah, at x1 and x2, and then we can take the induced flows on the manifold. And I mean, I want to sketch the idea first. So, I mean, when there's a pair of loops, kind of gamma sigma, yeah. So a loop in the product is of course a pair of loops. When does this have a self-intersection? Well, if both loops have a self-intersection at the same time. Yeah, but now I can deform all loops like uniformly in the following way. I mean, if this is gamma and maybe this has a self-intersection, well, then I can take the flow of the vector field, yeah, and I mean, recall that it's nova vanishing, so I go a bit in this direction, yeah, and then I go back again. I mean, along the same vector field actually, but yeah, I wanted to kind of make this clear, yeah, and maybe I do this in the interval. Maybe I do this kind of in the interval 0 to 2/3, yeah, and then in the interval 2/3 to 1, yeah, I go around the original loop gamma, yeah, and then on the for the loop sigma, well, I mean, maybe if this can have even more self-intersections, maybe I do it the other way, right? Maybe I go around the loop in the interval 0 to 1/3, and then I go along the flow of the vector field, and then back again. Yeah, and of course, since these vector fields are nova vanishing, then in these intervals, so here 1/3 to 1, I have no self-intersections. Yeah, so then on this pair of loops, I got rid of all the self-intersections. Yeah? And okay, I mean, you can write this down explicitly, but the formulas now are not so interesting. So the point here is we can define a map, yeah, which goes from lambda n to lambda n. And well, I mean, here we stick this flow to the loop gamma, yeah, and then here we go around gamma, and here we do it kind of the other way around. Yeah, and I mean, this is just kind of sticking kind of a short loop to the base point. So this is certainly, I mean, like up to homotopy we didn't do anything. Yes, so this is homotopic to the identity, and each loop in the image has no non-trivial self-intersections, right? Because of this, these are nova vanishing vector fields, and well, then we see that every homology class actually has intersection multiplicity 1. Yeah, I mean, so sorry, now I wrote homology class in non-relative homology. There you can also make this definition, and then if you show this, then it's actually also, of course, sufficient for showing this for the homology classes in relative homology. Yeah, so we have shown that the intersection multiplicity is 1, and consequently the coproduct vanishes. Yeah, and this is maybe already, I mean, the proof is very naive, as I said, but already it gives you something which I found interesting. So if you look at, sorry, my writing is terrible. If you look at products of odd dimension spheres, yeah, we know that on each factor, yeah, the coproduct is non-trivial, and so then on this product we get a trivial coproduct. Yeah, and again, this behaves very different now to the Sullivan product, which is, yeah, in such a situation, just the tensor product of the individual Sullivan algebras. All right, and yeah, so this was about the coproduct on the free loop space, and now like a related result, but where we can only do it for the based coproduct, and you will also see why. So if we have a smooth fiber bundle, yeah, and we will be interested in the coproduct on the total space, yeah, but we need this setup. So we have a smooth fiber bundle, yeah, everything, the total space, the base, and the fiber are closed-oriented manifolds. In particular, I don't want kind of coverings or anything, so I want everything to be connected. Yeah, and I also don't want the identity map or the map to the point. Yeah, so I really want to have an interesting fiber bundle. This is just what this says here, that the dimension is positive. And okay, now assume that this is the important part here. That assume that this fiber bundle has a section. Yeah, and then the statement is then every class in the reduced homology of the base loop space has intersection multiplicity 1. Yeah, and consequently the base coproduct on this total space vanishes. And of course, this includes then all product spaces, yeah, without a restriction of the Euler characteristic, as in the previous theorem. Yeah. And okay, so let's see how this works. I want to sketch the proof.
Is the idea somehow that this fiber direction allows you to sort of remove the intersections?
Yeah, yeah, exactly. Yeah, I mean,
okay,
you would see, yeah. So okay, but so the setup you need to make is the following. So we can loop this fiber bundle once, then we get this looped vibration here. Yeah, this then we get this in the long exact sequence of homotopy groups. Yeah, I mean, you can also loop the section. Yeah, so you get a section here of this looped vibration. Yeah, so you get sections in each for each eye of this long exact sequence. Yeah, so you get many short exact sequences which are split. And so we get nice isomorphisms here from the isomorphic group of omega E to this direct sum of the isomorphic group of omega B, direct sum with the isomorphic group of omega F. And of course, we know that, I mean, this direct sum is isomorphic to the isomorphic group of the product omega F times omega B. Yeah, so far so good. But the point is that—
quick question.
Yeah.
Does the section have to be non-vanishing? Or can we have zero?
I mean, it's not a vector bundle, right? I mean, this is just any fiber bundle. So, I mean, don't think of vector bundles. I mean, I want the fiber to be compact. So, I don't know, think of a sphere bundle with a section.
Right. Okay.
Yeah.
Thank you.
Yeah. Thanks. Yeah. Thanks for the question. And okay, I mean, the point is that this isomorphism, we can actually make it more explicit in the following sense. So we can write down a map G from this product omega F times omega B to the base loop space of the total space. Yeah, and now, I mean, now you can write down the following. So you take a loop gamma in the fiber. Yeah, I mean, this of course then also lives in the total space, and a loop in the base you can lift to the total space with the section S. Yeah, so I mean, everything is based here, so this concatenation is well defined, and then you can check very easily that this map induces this isomorphism in homotopy groups. Yeah, and now, well, okay, so now we've seen that this map is a weak homotopy equivalence. Sorry, there's missing two. This goes to omega E. So this is a weak homotopy equivalence, and well, it's a result by Milnor that loop spaces of closed manifolds are CW complexes. Yeah, so G is actually a homotopy equivalence. And now, as already kind of asked earlier, so now the idea is kind of now we have this kind of many directions, and now we can deform the loops in the image of this map such they have no base point self-intersection. Yeah, and so okay, maybe what's the idea here? So well, the loops in the image of G, what do? Well, in the first half of the interval, they run only in the fiber direction. Yeah, and then in the second half, or maybe I shouldn't use red and green. And then we run only around the base, or I mean, if this is kind of the section of the base. Yeah, and then, well, now we can just work locally around the base point, and we can write down a deformation kind of this coordinate cross, if you will, yeah, which looks like this. And you can do this in a kind of if you want, in a smooth way, and you can do it in a so you can kind of, I mean, there's a homotopy to the identity, and so then you can kind of turn on and off this deformation using the time parameter of the loop. Yeah, and like this you can remove all the self-intersections and for these base loops. Yeah, and it's quite clear that, I mean, this strategy does not work immediately on the free loop space, but in the setting of the base loop space it works. Yeah. And again, then you show that this shows that the intersection multiplicity is 1, and this gives you then this statement that the base coproduct on the homology of the base loop space of this total space E vanishes. Yeah, and I mean, maybe then as a kind of corollary, of course, you get the converse statement.
So hold on. So this is like a good generalization of this Euler characteristic 0 thing, though, right? Because like there, you could look at like the unit sphere bundle, and because you have a section to a nowhere vanishing section in the tangent bundle, you can get a section to the sphere bundle. Like, does this result, like you're saying, implies the previous one, though, right?
No. Sorry, I never wanted to say that. Yeah. No, I mean okay. These are. The first result was on the free loop space. Now we're on the base loop space. But I mean, of course, now we have a bigger class of. I mean, in particular, I mean, this is also obvious corollary, right? I mean, now we can look at any products, right? I mean, any product space is a total space of a fiber bundle with a section, trivially. Yeah, but it's even. I mean,
right.
Yeah, and of course, I mean, maybe also here this converse here. I mean, if we have a closed-oriented manifold with non-vanishing based coproduct, well, I mean, then in a sense we have an obstruction of this to be the total space of a fiber bundle with a section. And I should actually add, of course, it can still be a covering or something, but it cannot have like positive dimensional fiber and base. Yeah,
that's pretty cool. I mean, that doesn't seem easy to sort of obstruct in general, right? I mean, that's like a hard thing to say you're not one of those, right?
Yeah, I mean, so I think, I mean, this kind of, I mean, I think this is quite a large class of spaces that can be total spaces of fiber bundle with sections. So, if I put it this way, then, I mean, and I mean, I want to say that, I mean, the only examples that I know where the base coproduct is non-trivial are also these, I mean, spheres and projective spaces. And of course, I mean, for these spaces, I mean, I guess you have different tools to show that they cannot be the total space of a fiber bundle with a section. Yeah, but, okay. All right. And so again, I mentioned this corollary because, I mean, here it says base coproduct. Yeah, previously I was talking about the coproduct on the free loop space, and there I had to make this restriction on the Euler characteristic. All right. Okay, so far, basically, I mean, in a sense, both of these proofs were relatively naive, right? I mean, you really wrote down deformations. Yeah. So.
Question. If the coproduct for the free loop space is non-zero, does that imply that the coproduct for the base loop space is non-zero? Is that direction? No. And do you have examples?
Yeah, products of even dimensional spheres. So I mean, the free coproduct is kind of almost trivial. Yeah, but there are some classes where it's non-trivial.
Let me think. So the base wait, what's the claim for this? Sorry.
So this has coproduct non-trivial, but base coproduct trivial.
I see.
Yeah. All right. Okay. And any further questions at this point? All right, then I guess I have like 20 minutes left, so I can still talk now a bit more about the more geometric situation. So eventually, I want to come to Lie groups and also talk about symmetric spaces now, how can we understand the free loop space of these manifolds? Well, one way is by looking at the Morse theory of the energy functional, and this of course involves geodesics. By critical point theory. So I want to give like a brief introduction now to these concepts. Yeah? Okay, so geodesics and loop spaces. And I want to recall that we look at this version of the free loop space with H1 regular loops. Well, one upshot was that we kind of now have a Hilbert manifold and can talk about submanifolds, finite codimension submanifolds. And the other upshot is that this is now easier to relate to Riemannian geometry. If you take a Riemannian metric on M, then we can define a function on the free loop space. People always call it functional, but it's just a real valued function on the free loop space. And what do? We take a loop, and then we integrate its the square norm of its derivative. Yeah, and this norm, of course, I want to remind you that this depends on the Riemannian metric. So technically, this depends on the metric. Yeah, so I should write EG actually. Yeah, and okay, and this is well defined. I mean, since we have this regularity assumption, and not only that, but it's also like a continuously differentiable function, or even twice. And then the point is, why do we look at this? Well, a point C is a critical point. Loop C is a critical point of this energy functional, if and only if C is a closed geodesic in M. Yeah. So what is a closed geodesic? Well, a closed geodesic is a geodesic that doesn't only somehow have a basepoint self-intersection. Yeah, so this would not be a closed geodesic. sorry, but it really closes up also with the tangent vector. Yeah, and since the geodesic equation is ODE of second order, then this really gives you a smooth periodic geodesic. Yeah, and these kind of geodesics, these are the critical points. If you restrict the energy functional to the base loop space, yeah, then you just have those geodesics that close up at the base point. But as I said, so they can kind of, you can get this picture. Yeah, so the tangent vectors don't need to align. All right, and okay, then of course, I mean, now we have a function, and we can have maybe a geometric way of understanding the critical points, and then of course, like we want to do more theory, kind of to understand maybe the homology, or to relate the homology of the free loop space to these geodesics, yeah, to the critical points. And okay, so I want to give a brief kind of overview over one way of how you can do this and how you can gain information from knowledge, geometric knowledge about the closed geodesics to get some homological output, or output about the homology of the free loop space. Yeah, and I mean, this I want to present in a bit greater generality. So if we look at the Hilbert manifold, and then we have a Morse spot function, yeah, I mean, a Morse function always has in particular isolated critical points. This never happens for the energy functional on the free loop space. So we have to look at Morse spot functions, where you can have higher dimensional critical submanifolds, but they also have to be non-degenerate in certain sets. Yeah, I don't want to talk about this in too great detail. But if you have a critical submanifold at a certain level, yeah, so f of this critical submanifold is A. This is what I mean by level. Yeah, and assume that this critical submanifold, I mean, you can associate a negative, so-called negative bundle, and if you assume that this is orientable, then there's an isomorphism of this relative homology to the homology of the critical submanifold with the index shift, with the degree shift. Sorry, yeah, where lambda is the Morse index, and here we have the sublevel set. And so these are all points in the Hilbert manifold with where f of x is less than or equal than a. Yeah, and of course x strictly less than a, you have the same thing but with a strict inequality. Yeah, and well, now the question is, I mean, in what situation is the homology made up from all these level homologies? So from these homologies here. Yeah, in general this doesn't happen. Yeah, the general picture could be like this. So you have kind of this deformed sphere. So this is supposed to be a sphere. Yeah, and then you have a critical point here of index 1, and okay, then I mean, then this critical point actually gets killed because you have kind of these gradient flow lines, and I mean, people that have seen Morse theory certainly know this picture. Yeah, so kind of here, I mean, this wouldn't be the situation where we are happy with respect to this question, but okay, let me draw a different picture. So if you have the torus, yeah, standing like this, and then you have this height function, the Morse function. Well, then the cycles that represent this relative homology, they kind of hang down from here. Yeah, sorry, I'm really bad at drawing, at least here on the computer. And okay, this is a relative cycle, but of course here on the torus we see that we can complete it, yeah, to an actual cycle. Yeah, and okay, now we want to have a setup where we can do this kind of yeah, in certain situations, and then the point is. Well, I mean, this is the idea. So if this negative bundle can be completed in X, then the relative cycle cannot kill anything. This is what I was trying to draw just now. And so that's why we look at the notion of completing manifolds. And since this is now important in the rest of the talk, I really want to give the full definition. Yeah, I mean, this idea of completing manifolds is, of course, older than the work by Nancy Hingston and Alex Wancha. But I mean, this definition that I'm using here is based on their work. Okay, so let's quickly go through it, and I will try to say what's really important here. Okay, so in this situation of the previous slide, assume that we have a critical manifold, and assume, okay, so we assume that the critical manifold sigma is oriented with index lambda and nullity mu. So nullity is in particular the dimension of the critical manifold for Morse spot functions, and then we want to define what a completing manifold is. Yeah, so this is a closed-oriented manifold gamma, yeah, of this dimension index plus nullity, and there's a closed submanifold S in there, and an embedding of the completing manifold into this Hilbert manifold, yeah, such that the following properties hold. So F maps S diffeomorphically onto sigma. What do I mean by this? Well, S is a submanifold of gamma. Yeah, so if you look at this composition, S goes to gamma, and then via F we go into the Hilbert manifold. Then we map S via this composition diffeomorphically onto the critical manifold. then we have a retraction, P, which, I mean, usually this is the fiber bundle, and S is a section of this fiber bundle. And then actually gamma maps into the sublevel set, and everything which is not in S, we should think about S as the critical manifold. Everything which is not in S maps to X less than A. And maybe another quick sketch. Now we put the torus like this, so that we have this S1 symmetry. So now we look at this height function, and then there are two critical manifolds, and one critical manifold is kind of these highest points here. This is the sigma is now S1, and then the completing manifold is actually the whole torus. So kind of this negative bundle hangs down here, and of course actually we can compute it. We just take the whole torus as a completing manifold. Okay, so just as an example, and well, I mean, what's the upshot here? So now let's assume that we are in this scenario. So we have a completing manifold for the critical manifold sigma, and we have this embedding. Recall also that we have a retraction, and then we look at these two long exact sequences in homology, of these pairs. So these two sublevel sets, the strict sublevel set, and this X less or equal than A. And here we look at gamma relative to gamma without this submanifold S. And then the vertical arrows are all induced by this embedding F. Okay, and I mean, the point is now we want to show that this connecting morphism is trivial. And so the best way, of course, is to come up here with a section. And indeed, we can do this now with our setup, because I mean, you can look at the following composition. So I mean, here we have an isomorphism. This is just a Tom isomorphism, basically. And then you can go like this. Then there's a Giesen map, because we have this retraction which goes in this direction, and then we can go up here. And this, like going along this blue line, gives you the red arrow actually, and this is indeed a section here. So you get, so in particular this implies that all the connecting morphisms vanish, and and in particular, of course, that we get the splitting here. So now assume that we are in a scenario where every critical manifold has such a completing manifold. Then we are in a scenario where the Morse-Bott function is perfect. And perfectness means, at least for me, that all these connecting morphisms for all of these sublevel sets are vanishing. And then in particular, of course, this implies that we get this, we get an isomorphism from the homology of our Hilbert manifold to this direct sum of all the critical manifolds. And I guess you have to assume that the function is bounded from below. So if this kind of maps like the energy function, if it maps into something like this, sorry, this is a round bracket, then you get this isomorphism. Okay, so far so good, but actually you get even more. You get very explicit injections. So we had this construction that we have this Giesen map, which goes from the homology of the critical submanifold to the homology of this completing manifold. So I mean, there might be situations where we can understand this very well, and then via this embedding we can go into the homology of X, and then the composition of this is also injective. And this is really, in a way, I mean, also if we understand this embedding, for example, in the situation of loop spaces, we usually can write this down explicitly, and then you understand kind of the image of the cycles that you are looking at. You can understand this very well. Okay, and I want to mention two results here from the literature, so which are very important, of course, in this setup here. So Bott already showed in the 50s that if you have a compact Lie group, then, I mean, to look at an energy functional, you need to say for which metric. And on a compact Lie group, there are bi-invariant metrics, which are like the nicest metrics. And then indeed, this setup works for the base loop space. Every critical manifold has a completing manifold, and consequently, the energy functional on the base loop space is a perfect Morse-Bott function with Z coefficients. I mean, or in general for arbitrary coefficients. I'm specifying the coefficients here because so Ziller then in a sense generalizes this or transfers this to arbitrary compact symmetric spaces, and then you don't have these orientability conditions are not satisfied anymore, so you only get this for Z2 coefficients. But this was still, I mean, this was enough kind of to make then certain statements about closed geodesics, where you can relate Betti numbers to numbers of closed geodesics, and then it's good enough to be kind of with Z2 coefficients. Okay, and well, now the idea is that we use, I mean, this, as I said, so this construction by Bott is very explicit. So the idea is kind of to use this to say something about the string topology operations. And okay, so I don't have that much time left anymore. So okay, maybe I will have to be a bit quick at some point, but so I wanted to present some details here. So if you have a simply connected compact Lie group, we take a bi-invariant metric, and for compact Lie groups, we know that they have maximal tori, and so this is a torus really as a subgroup of G, and this induces a corresponding maximal abelian subalgebra. And if we look at geodesics, well, then we can always kind of look at geodesics in the torus. If we look at any geodesic in the group, then we can actually conjugate it with the group element such that this conjugated geodesic lies in the maximal torus. And we also know that sigma of t is just a Lie group exponential of like a straight line in the maximal abelian subalgebra. Of course, the Lie algebra of the torus is of course the universal cover, and then the exponential map is just the covering map. Sorry, universal covering. Okay, and okay, now I need to talk a bit about some geometric input here. So okay, it turns out that there's a family of hyperplanes, and they are called singular hyperplanes. Singular is just a name. Inside this maximal abelian subalgebra, and whenever this straight line meets such a singular hyperplane for some singular plane, then sigma of t star, so the point on this geodesic, is conjugate to the base point, and of course as a base point we take the identity element in the group. And the conjugate point, this is a term from Riemannian geometry, that means that we have a geodesic between 2 points, and we find a continuous variation through geodesics of this geodesic, a non-trivial one, such that the 2 points where we fix the geodesics at its end point, and then we have a variation through the geodesics. And moreover, you can characterize these conjugate points by the fact that the centralizers of these points have larger dimension than t. For a generic point, the centralizer, the group theoretic centralizer is just the torus itself, and when the dimension jumps, then you get a conjugate point. Okay, so I mean, the main point is actually that I wanted to show some pictures. So here, I mean, this is kind of the maximal abelian subalgebra, and then this straight line here, this is just the t times x, if you want. And okay, then all these hyperplanes here are the singular hyperplanes. And okay, so this is kind of what the lift of a geodesic would look like. And then whenever we meet a hyperplane, we get a conjugate point. And now there's okay, so it's important that the centralizers actually don't really depend on the points, but only on these hyperplanes that we meet. So you can also move then kind of along the hyperplanes. And okay, now this construction by Bott goes as follows. So for each finite families of singular hyperplanes, we choose a path that goes from one hyperplane to the next. So for example, you can take this family here, delta 1, delta 2, alpha 2, delta 3. And then we need to go from the, I mean, we want to have a loop in the end, so we need to start at the origin, and then we go from one hyperplane to the next. And it might happen that we cross some other hyperplane, but that's okay. And then every time we meet a hyperplane, we vary the corresponding path in the maximal torus, or then in the Lie group, by all variations coming from this homogeneous space. And this homogeneous space, that's what I was trying to sell. This has positive dimensions, so these are non-trivial variations. And then then you take kind of this product, and then you quotient out R copies of the torus. So this is not the R torus, but R copies of the torus, which has the dimension of the rank of the group. And this can be used as completing manifolds. I mean, of course, I'm being a bit sketchy here, but the point is this picture. And well, a priori, it can happen. Okay, so now when do we get? Sorry, let me start differently. So as I was trying to tell you, why are these completing manifolds? We get very, very explicit cycles that generate all of our homology. And then, of course, we can ask, okay, can we again do this trick that we remove the self-intersections? And if the rank of the group, so the dimension of the torus, is indeed greater or equal than 2, then you can actually do this, right? I mean, because when do we have self-base point intersections? Well, if we meet the lattice in the universal covering here. So it might happen that, okay, at this point here, okay, we meet the lattice, but it's not important. So, I mean, this is where several hyperplanes meet, but okay, we are allowed to move this along this hyperplane delta 2. So we can move it away from this intersection. And okay, and then we end up with, so this path is also possible to use for this completing manifold business. Yeah, and then okay, then we see that we remove this from this lattice point here, and then correspondingly the curves in the Lie group, so in the image of the cycle, the loops have no base point self-intersections anymore. Yeah, and so then we get the following. Okay, so far I've only also talked about the base loop space, but the nice thing is that for Lie groups, the free loop space is just the product of the Lie group and the base loop space. Yeah, and moreover, Bott has also shown that the homology of the base loop space is free. Yeah, and thus also with integer coefficients we have an isomorphism here. Yeah, and I mean, since this is this homeomorphism here is very explicit, we again get kind of very explicit, can very explicitly talk about our cycles in the free loop space that generate the homology. And then indeed we get that for simply connected Lie groups of rank r greater or equal than 2, yeah, all classes of intersection multiplicity 1, and correspondingly the Goresky-Hingston coproduct on G vanishes. Okay, and yeah, I mean, note that the 3-sphere is also a Lie group of rank 1, yeah, which has a non-trivial coproduct, and so this restriction on the rank is necessary. And of course, I mean, the same trick, if you have rank 1, then your maximal torus is the maximal abelian subalgebra is just a line, and the singular hyperplanes are points. And if you have a path from the origin to some lattice point, yeah, then of course you cannot remove this self-intersection. Yeah. Okay, and okay, just for I mean to show you, I mean, there are many examples of higher rank Lie groups that we like very much. Yeah, so the special unitary groups for n greater or equal than 3, or the spin groups, so the universal coverings of the special orthogonal groups. Okay, so now I will try to wrap up. So we'll skip a bit. Yeah, maybe, so here I just wanted to say, so Hepworth shows that for the Ch-Sullivan algebra, there's an isomorphism for Lie groups between the Ch-Sullivan algebra and the tensor product of the intersection algebra and the Pointryagin algebra, yeah, which is well known to be non-trivial for basically yeah, for all Lie groups, yeah, and it's also explicitly computed also by Bott back in the 50s. Yeah, so this is also a bit puzzling to me that the Ch-Sullivan product is non-trivial on Lie groups of any rank, but the Goresky-Hingston coproduct on higher rank Lie groups behaves very differently. Okay. And so then, yeah, just to mention this triviality result for the base loop space, this carries over if you restrict the Z2 coefficients also to arbitrary compact Riemannian symmetric spaces. Yeah, so this construction by Bott works in exactly the same way. What you don't have is this isomorphism. Yeah, so if on arbitrary manifold, of course, it's not true that the free loop space is the product. Yeah, so this doesn't work anymore. Yeah, but so just quickly here. So if you have a compact Riemannian symmetric space of higher rank, then also this base coproduct vanishes. Yeah, and okay, so in this sense, the result can be transferred. And okay, then okay, I have kind of another result on the next slide, but it's maybe would be a bit too much to look at it. So I also have a result where I use these explicit construction with completing manifolds to compute the coproduct on complex projective space, yeah, and on quaternionic projective space. So just to say that you cannot only show that the coproduct is trivial with this, but you can also like this really also sees the structure kind of the coproduct these completing manifolds do if you have also in this situation where the coproduct is not trivial. And so I want to skip this slide, but what I want to mention maybe quickly, briefly, are a few questions. So, I mean, I think in general it's interesting now to ask, okay, for which manifolds is the coproduct non-trivial? Yeah, somehow, I mean, at least to me, it was a bit unsatisfying actually that for Lie groups at least, it would be nice that the coproduct, yeah, would be non-trivial. And I mean, maybe in particular, this is also a question which would be interesting in the non-simply connected setting. Yeah, I mean, of course, this as we discussed, this spectral sequence maybe doesn't work here. But I mean, why am I mentioning this? Well, I mean, on this formula for the non-homotopy invariance, I mean, we don't want to have 0 equals 0 on the left and the right hand side. Right, and I mean, there is this example, of course, by Florian Neff for length spaces where the coproduct is really non-trivial, but yeah, maybe this is a reason to also think about this a bit more. And then well, then of course people are very interested always in higher operations, or I wrote other coproducts, but maybe you should think of higher coproducts. Okay, maybe actually in these situations where I showed you that the Goresky-Hingston coproduct is trivial, maybe there's kind of some other coproduct or higher coproduct, if you want, that is not trivial. I think this would also be interesting to see. And finally, and this is also quite puzzling to me, so I mean, people are interested in considering kind of both the Sullivan product and the Goresky-Hingston product or coproduct as part of somehow one big structure. Yeah, just to mention a few papers here. So that by Chilibak, Hingston, Wanscher, and by Lachev, Wanscher, there's work in this direction. And I mean, they usually don't consider directly the Goresky-Hingston coproduct, but at least in Chilibak, Hingston, Wanscher, they actually they in some sense, if you want, they enhance this construction a bit, and but still then they somehow get some duality statements between the product and the coproduct. And of course, in the results that I showed you, I mean, it doesn't look at all like duality, right? For example, higher rank Lie groups have non-trivial and nice Sullivan product, but trivial coproduct. So, and yeah, I want to stop here. So thanks for your attention.
Thank you. Let's thank Maximilian. That was an interesting talk. Were there any questions? I have a quick first. Ralph, do you want to? Mine is
maybe the same thing. So a quick question, comment. So Manuel and Zhengfeng Wang and also with me have also a nice package of these operations that fit together. And then so there's another example of that. And one thing that's interesting is that there are higher operations there, which are obstructions to. So the way to think of these operations is that they give their boundary gives you some relation between products and co-products and so on. So you have some equations. And basically, so that was the comment. So these kind of higher operations exist. One should see what happens. And then the comment is, you can take the Goresky-Hingston coproduct actually, because it's not closed, you have to make it closed as a cycle to descend to cohomology, right? It is a chain operation anyway, and then you modify constant leaves to make it. So you can think of that as sort of an obstruction from left multiplication by constants is equal to right multiplication by constants. So if you, in a sense, when you're saying, so you had these results that, you know, whatever this Goresky-Hingston coproduct is 0. So more or less, I guess you're saying some sort of implication if this thing is 0, then left multiplication is right multiplication. So, you know, that goes a little bit the other way around, but you had some results with constant loops, or I forgot the constant product being sort of commutative. So this is one of the things that, you know, if that's 0, then that obstruction vanishes, and then left multiplication by constants is right multiplication by constants. So you can ask otherwise around, if left multiplication is right multiplication, then the connecting cochain or whatever doesn't have to be 0, but it can be. And then if you have these vanishing results, I'm wondering that if this chain giving you the Goresky-Hingston coproduct, if you're saying that, you know, this is a boundary of something, and that operation is 0. So that's something to think about, because that would be sort of an algebraic reason why these things are true. And then you found these wonderful examples where all of this is true, but maybe this flow actually just tells you that, you know, you can contract that obstruction to that thing vanishing. That's just a comment. So
it's like Chern-Simon's theory, you know, like the way something becomes trivial often has geometric meaning, right?
Yeah. So maybe it's sort of interesting from that fact that that thing vanishes. That you have some operations which then, like this thing actually commutes on the nose, right? I mean, the abstraction where you had to call, you know, to make Goresky-Hingston into a cohomology operation, then you had to mod out by constant loops. And you're saying if it's 0, I don't have to. Well, that's the whole point. And then you get this bigger structure on the thing where you don't mod out. So stuff like that. That's interesting. I mean, maybe Manuel can send you his papers or our preprint or something like that.
Well, yeah, I mean, my feeling after thinking about this for a few years is that these higher operations, the ones Ralph was mentioning, you know, you have compatibilities between the Chas-Sullivan product and the Goresky-Hingston coproduct that satisfy up to some higher operations, and these seem to depend on moduli of the moduli space, you know. So I think these might have geometric meaning even in the case when the coproduct is trivial. So it would be a good project to compute this for Lie groups, for instance. I mean, I have no idea. Like
Yeah, I think maybe something like this would be interesting to actually see.
Yeah,
this.
in particular, there's this bi bracket which you get from sort of dualizing the thinking of the coproduct and the product, and then there's a weird compatibility which this bi bracket actually gives you sort of homologically, because it's
these are non-trivial even in the simply connected case, because that's the setting that I were working in. So already there, it's a.
And that's sort of interesting. You know, what can you say about these things if half of the structure is zero, or you know, homotopically is zero?
Yeah.
I see. Yeah.
Then my comment was, or my question, how does intersection multiplicity interact with energy? Is there any relation? Like,
well, I mean, you can give some bounds, I guess. So, I mean,
if the energy is higher, what does that imply about if anything, about intersection?
Well, I mean, in general, well, okay. So I would say that there's, I mean, if you bound the energy, then you get some bound on the intersection multiplicity, because I mean there are these finite dimensional approximations of loop spaces, and then you can only have kind of as many intersections as you. I mean, then you can. I'm sure you can write something down which bounds the. So this would kind of involve the energy and the injectivity radius. I think you could write something down like this. I mean, of course, you don't get any lower bounds, right? I mean, on Lie groups there are classes that have to have arbitrary high energy, but they all have trivial intersection multiplicity.
Right.
So
this is interesting. I mean, this relates to what we were talking about at the beginning. So there's this. I mean, I'm repeating this because some of my string topology friends here are not aware of this. So there's this paper. It's an Invenciones paper actually of Moira Chas and some statistician from Chicago, which I forget his name, which kind of analyzed the distribution for surfaces. So they analyzed the distribution of this intersection multiplicity for curves on surfaces.
Yeah, these things have been studied. There have been other papers. This is a very, very popular subject. The thing going back to this sort of energy versus sort of intersection. I mean, intersection is like a topological complexity, and this sort of energy is a geometric complexity. And so the best you could ever hope for is that the topological complexity gives you kind of a lower bound for the geometric complexity, or the geometric complexity gives an upper bound for the lower. So like if you have an upper bound on the energy, then you can get an upper bound on intersections, but you can never hope for the converse, because you can make things geometrically as complicated as you want in some sense without somehow making it topologically complicated.
But then
that's sort of just geometry.
There's this result, so maybe I'm misstating it. For curves on surfaces, it says something like the distribution of intersection multiplicity with respect to something like energy, which is word length of something.
Or length, just like the length of you could just take length of geodesic or something.
Right, but then they show it's normal. It becomes closer to a normal distribution if something happens. I don't know.
Yeah, I mean, it comes closer to being normal as the
length goes to infinity.
The length goes to infinity.
Because the idea is that like as you allow the length to go to infinity, okay, you look at all the geodesics up to that length. There's only finitely many of them, right? And you could you could look at the self-intersections of each one of them and sort of see how they distribute. And you would definitely expect it to distribute normally, right? Because of like ergodicity or something, you know, like, I don't know. Like,
so it feels Ben, do you think something like this is true for three manifolds, say?
I would suspect the same thing.
Okay, interesting. Good.
Also, I mean, I like Lie groups. So, I mean, if you guys are interested in computing these things for Lie groups, these higher order operations or whatever,
we should all do it.
That sounds very interesting. Also, I have some other ideas too on these loop things that because one of my PhD students or former PhD students is very good at rough paths, and rough paths are like another way to sort of get at like loops and stuff. But it's a different kind of analytic tool. Instead of going to a Sobolev space, now, you're working like the rough paths just give you sort of like, Taylor series coefficients, but via integration, iterated integrations and stuff. And so, but there's lots of cool stuff there too. But this loop stuff, it's sort of interesting. It's also not surprising that you'd have this divergence of behavior with real rank 1 versus higher rank, because that's an incredibly common theme, when it comes to like semi-simple Lie groups, like,
Sure,
real rank or just these spaces and stuff. I mean, I guess you're just the idea there, though, is that once you have at least real rank 2, it just gives you that extra room where you can remove these intersections. Is that like the idea again?
Yeah, that's exactly the idea. Yeah, of course.
You just always, if you have that extra room, like when you had the flow or when you have the fiber, then you can sort of remove those intersections.
Then there's maybe another question that's also good to mention here in post, which is the converse of many of the things you were using, like vanishing of iterated coproduct. What does that imply about intersection multiplicity, right?
Yeah, so I mean, then things naturally well, they have the result that for spheres and projective spaces, this is really an equivalence. Maybe I can show this theorem again.
Right. Then for curves on surfaces is still open. At least it was open maybe like 5 years ago. Like if is my student here? No. If the twice iterated co-bracket for curves on surfaces is 0, it's not known if you can represent your curve.
Then it should be simple.
Yeah, it should be simple, but I think it's not known. It's open and it's been computed for a bunch of cases to be, and it seems to be true.
That one also sounds very interesting. I've thought a lot about curves on surfaces, and especially simple curves, just because there's some interesting conjectures in spectral geometry whether or not the lengths of the simple curves on a surface should determine the hyperbolic structure. And it's different. Like the lengths of all like when you have length isospectrality, like you have a bijection between the lengths of the geodesics, it doesn't respect the topology necessarily at all, and it definitely doesn't respect like how the curves are configured on the surface, because those things, of course, determine the surface. Just like in the sense of like like the Jacobian with the the intersection pairing, which gives you the symplectic form, right? Like that. Knowing the lengths of the curves and how they intersect determines the hyperbolic structure. But
Ben, can I share some something here in my screen? I mean, it's just an abstract, but
sure.
This is the best. This is the best known result about characterizing simple closed curves in terms of brackets. So you see, so
in terms of this stuff.
So computer search have verified this conjecture. If the twice iterated co-bracket vanishes, then it can be represented by a simple curve. That's what derived 2 means for hundreds of millions of the shortest classes. But
I don't know. Those things always. The thing is I believe that there's this. I guess this sort of conjecture is plausible, right? Like simple curves are really important. They are like topologically important, and you should be able to witness simplicity by this sort of method, right? Like some kind of idea like this. And so,
maybe
I think
this
it's a
method
very
is
plausible
impossible
thing,
to.
right?
maybe it's impossible to compute in practice this method, right? So it's like,
yeah, I mean,
know.
I suspect, well, always to me, the best idea is to try to find another idea to go along with this that's kind of outside what these other people would think about or try, because, you know, if people have tried, you know, in the area, they're going to try all the things that the people in that area would try mostly. You would think that. And so usually you need a new idea or another idea. I mean, there are many problems, I'm sure, you know, if you work on problems enough, I mean, you'll have a really good idea and you'll think, oh, wow, this is going to solve it. And then you see, ooh, no, I need another really good idea too, at least. And that's, you know, I love problems like that because they put up a fight.
Yeah. Anyway,